Hello everyone, welcome to the project video for group Kunkun. In the next 20 minutes, we will introduce our progress of this project. For the first part, we will have a tour of the team's GitHub repo and mainly focus on files we made changes. The first folder is the workflow folder, which consists basic CI test commands for GitHub. The next one is the CI folder, which includes CI test code and necessary config to build a CI environment in GitHub. For example, the create local table.sh here creates DB tables for S3, and in the v1.1 folder, we added the Docker file to add command and parameters to run CI test for S3. And compose.yaml is responsible for setting up an integration test of S3. The next file is conf.test.py, in which we add S3 address, port, and URL. We also add create comment tables for CI test for createtables.py, and add S3 directory paths for flake-dirs.txt. The main point in this folder is comment.py and testcomment.py. Comment.py contains Python API for our new service. The testcomment.py contains the actual test code for testing services. They are the most important parts of CI test. In the same way, we have music and test music, user and test user, 4 different Python files to test services, music, and user. These are all about our CI folder. Let's get back to the main directory. The next one is cluster folder. It contains all the config we need for running our project in AWS. It includes 4 paths, config for DB, S1, S2, and S3. Also, we add the config for AWS table in CloudFormation DynamoDB.json and comment header file for config map built from comment CSV. That's all for the cluster folder. Then the folders DB, S1, S2, S3 represent different services, but most of our changes here focus on the S3 folder. S3 folder contains the new microservices comment. In this folder, we have 2 subfolders, V1 and V2. They are separate for convenience of blue or green deployment, but they share almost the same contents. In V1, for example, the Docker file here is for command and port to run the service, and the app.py file consists the actual RESTful API for service S3. Requirements.txt designed for loading the necessary packages of S3. That's all for the service folder. After introducing the service folder, let's get back to the Gatling one. As you can see, there are 3 subfolders here. We made change to the read tables in simulations folder to add table read for S3 and add Gatling test for comments which simulate 100, 500, and 1000 users access comment service in test folders here. The loader folder is an important folder to load our example data for our service. Here, we add loader for comment.csv in app.py file. The last folder I want to introduce here is mcli. The mcli.py in it has clients of S1, S2, S3, and a new monitor to the new service S3. Having looked at all the important folders, let's look at those makefiles we use. We only have changes in EKS and Kubernetes makefiles. For EKS, we update the configuration for the AWS cluster to satisfy the service requirement for 1000 users. And in Kubernetes, we add circuit breaker for S3. We will introduce how to run the project through these 2 files in the following part.
After the team setup, we select Danley as the product owner and Sijia as the Scrum Master. Our team planned 3 sprints. In Sprint 1, Danley arranged issues for Sijia and Jingshan. Sijia is in charge of initializing our GitHub repository and organizing daily group meetings. Jingshan is in charge of develop Server 3 and run S3 on AWS. In Sprint 2 and 3, Danlei and Yizhe are responsible for Gatling and Grafana and also the testing. When we encounter problems that cannot be solved by one person, like issue number 40, the story owner will assign the issue to our Intel team and we can solve the problem together. Now all the issues are closed and our project is finished. The next will show the deployment of our system into an empty cluster.
The next part is about how to deploy our system into an empty cluster. First, go to our project view and use this command to start a container. Next, use make templates to initialize the template fields in the project, such as eks.make and the template fields in the cluster. Then we start an empty cluster, which usually takes more than 10 minutes. When the cluster is started, it will display context renamed to AWS 756. Before we deploy the service, first we should check if DynamoDB already has the tables we need. Use this command to list all tables. You can see that DynamoDB currently has 3 tables: comment, music, and user, which are corresponding to our 3 microservices. Kubernetes uses a namespace to organize applications. We should create a namespace and set it as the default. Next, use provision to deploy our service to the cluster. We added commands to get Grafana URL and start clearly to the provision command. When the provision command completes, we can see that the Grafana URL and clearly URL printed on the command line. Open the Grafana panel with the default username and password. At present, you can see that the monitoring panel of each service on the left has no data. This is because we haven't added any load yet. The data can be seen in the cluster monitoring panel on the right. Next, we also open the Keoli monitoring panel to see that the 4 microservices DB, S1, S2, and S3 are currently running. Using get pods can also query the running status of each pod. The next part is about add load. Next, we should open a new window and enter Gatling test, which contains the Gatling test script we wrote before. First, we use Gatling 100, which can apply a load of 100 users separately to the 3 microservices S1, S2, and S3. When the load is added successfully, we switch back to the Grafana monitoring panel. We can first observe that the cluster monitoring panel on the right changes first, and the memory usage and the CPU usage started to rise. Next, data appears in the service monitoring panel on the left. It can be seen that within 1 minute, the number of requests for the 3 services is about 2.6 thousand, and the number of requests for DB is the sum of the number of requests for the 3 other services. When the load is 100 users, we can see that the number of successful requests per second is around 264, and no request errors occur. But the response time of the 3 services is about 1.5 seconds. Cancel the 100 user loads. You can see that the request data starts to fall. and then enable 500 user loads. You can see that the errors have started to occur, and the number of successful requests is also much lower than when the load is 100 users. Use a load of 1000 users. The number of successful requests per second continue to decline, and the number of error requests remains at a high level. The request response time is basically more than 10 seconds. This means that our current configuration cannot handle the load of too many users. The reason here is that the number of pods we assign to each service is only 1, which cannot handle too many requests. We should change the replicates of the DB to 160, and the replicates of the other 3 services to 53. Use make scratch to clear the existing deployment and use provision to redeploy our services after changing the configuration. It can be seen that the number of pods deployed by each service has changed, but most of the pods are in the pending state. This is mainly because the cluster has no actual CPU to allocate to these pods. Open the eks.make, and we can see that the current cluster configuration uses 2 instances of T3 medium. In order to improve the ability of our service to withstand the load, cluster configuration needs to be changed. We restarted the cluster with a new configuration, using HC6A 2x large instances, which means our cluster now has 64 vCPU. We follow the previous steps to deploy the service and open Grafana and Curly. We use getPods to see that all pods are already in the running state. When import 500 user load, it can be seen that there was no error in the system at the beginning, but after running for a period of time, the system began to crash, and the number of errors requests increased. The number of successful requests dropped sharply. At present, we have solved the bottleneck problem of services and cluster, and now the problem mainly lies in the database. The configuration of database can be changed in cluster CloudFormation dynamodb.json, but it is also possible to change the read and write limit of database directly in DynamoDB in AWS. We go to the DynamoDB page, click Tables, and click one of the table. Click Additional Settings. We can see that we can edit the read and write capacity. We can see that the capacity mode is provisioned and the read capacity unit is 5 now. We can make it larger or use the auto-scaling, but for convenience, we can use the on-demand mode provided by AWS to replace the provisioned mode. After changing the configuration of the database, we switch back to the Grafana panel. We can see that the number of successful requests has increased sharply, and the number of successful requests per second has reached 2.2 thousand, and the number of fall requests has decreased to 0. Next is the system running stably for 5 minutes. And this is a load test of 1,000 users.
Now I want to introduce load simulation with disturbance and some deployment ways. And first, I will add a network fault. Let's look at Grafana, and we can see all the services correct. Then I will add a fault through the config file, which is dbvs fault.yaml. I make 5% of the DB request return 500, and then let's restart the service. Okay, then we still look at Grafana and wait. Yeah. Since all the service require the DB service, so we can see 5% of the requests will return correct and 5% of the requests will return error. And then I will use the correct config file to restart the DB service. And still we can look at Grafana and we can see the service back to normal. And then I will add a network delay. Still first, let's look at Grafana and we can see all the service is correct now. And we can look at the config file. And this time I will use dbvs delay.yaml to add delay. I will make 50% of the DB requests delay by 5 seconds. Yeah, and then let's look at Grafana. And since all these service requests require the DB service, we can say the median of the requests returned is about 5 seconds. Then I want to test the timeout function. I will add timeout equals to 3 seconds in the service 3. And I will use the config file s3vs.yaml. And then I will redeployment the service 3. And this time we can look at Kelly. We can see there is some error in service 3. Then I will change the database to no delay and restart this DB service. And still let's look at Kelly. And we can see service 3 is back to normal now. Then I will introduce circuit breaker. First, I will add some error in the service, because only errors will trigger circuit break. So still this time I will use config file dbvs fault.yml, and this time I want to change error percentage to 100. Then I will deploy this service with error. Then let's look at Kelly, and we can see some error here. Then I will add a new configuration file, which is s3 vs circuit.yml, and I will add these parameters here. And it means that in the interval equals 10 seconds, and when consecutive errors equals to 2 is reached, the circuit breaker will be triggered, and the circuit breaker duration base injection time equals to 30 seconds. And then I will change the service series config file to circuit breaker, and I will deploy it. Let's look at Kelly and wait for some time. We can say service 3 is circuit break, and then I need to recover it. So I will use a write db config file, and to make sure there is no fault in the db, and I will deploy the db again. Then we will still look at Kelly and wait for some seconds, and we will find service 3 is recovered. Then I want to introduce canary deployment. And first we can see that we have 2 versions of service 2, and currently running online is version 1. And I will deploy version 2 use canary deployment. First, we will introduce a bug in version 2. So 50% of the request will return an error. In the config file, prevention canary, we have 90% of the traffic going to version 1 and 10% of the traffic going to version 2. And then I will deploy this new version. Let's look at Kelly. We can see that version 2 has some bugs, and half of the requests return error. So we will roll back and hotfix right away. Yeah, first I will reroute to version 1 and deploy it. And then I will fix the bugs in version 2. Which here I will change this 50 to 0 or less than 0. So still use prevention canary this config file. I will deploy the service again. let's look carefully. We can see two versions can work normally. So this means version 2 is okay now. So we will delete version 1 and let all the traffic go into version 2. So this is a canary deployment. We also do like a blue-green deployment, and I will not introduce it this time. So you can see it through our reports. That's all of my part. Then I will simulate machine failure. First, we will see all the pods are running normally. Then we go to AWS and stop 4 instances. Still look at the state of the pods. We can see some pods are terminating. Then we go back to AWS and start all the instances again. Look at the pod state. They are back to pod initializing.